Okay. Um, so if I remember correctly, this is where we stopped the last time. Please correct me if I'm wrong, but I think this is where we stopped the last time, right? Okay. So I think the next slide is an example. It says, write the electron configuration of the cobalt 3 plus ion in a noble gas core, abbreviated SPDF notation. So basically, I think I told you guys before, if you want to write down the electronic configuration of an ion, then you start off with the atom first. Cobalt, I don't have a periodic table with me. Can you see what the atomic number of cobalt is for me, please? 20 what? 27. All right. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d7. All right, so that would be the electronic configuration of the cobalt atom. So to get from the atom to the cobalt 3 plus ion, we have to remove 3 electrons. So the question now becomes which electrons will be removed first. And if you remember, I said that when you're trying to find the cation electron configuration, you start removing electrons from the shell with the highest quantum number, which in this case would be the fourth shell, right? So that means that 2 of these electrons will be removed, right? And then the next in terms of energy would be the third shell, and you have these sublevels within the third shell. You start removing from here, which is the highest energy subshell within that shell. So therefore, you're going to remove 2 of these here. You're going to remove 1 of these, leaving behind 6. So therefore, the electronic configuration of cobalt 3 plus would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d6, and that's it. All right, and that would be the electronic configuration of the cobalt 3 plus ion. All right. Oh, not finished yet because it's asked for the abbreviated. So if you remember, to get the abbreviated version, we have to go to the periodic table and look for the group 8 element that immediately precedes cobalt. And if I'm not mistaken, that's argon, right? Right. So argon would basically have this electronic configuration here. This would be the electronic configuration of argon. So the final answer, which would be the abbreviated configuration, would be this. 3d6, and that's it. All right? So that's how you get the abbreviated SPDF notation for the cobalt 3 plus ion. Okay, any questions about this? Any questions? Okay, so let me move on to the next slide. So now we're going to talk about magnetic properties, all right, as it relates to the electronic structure of atoms and ions. So there are 3 types of magnetic properties that we're going to discuss, but one of them will take precedence in terms of importance. You have what is called diamagnetism, which is a weak repulsion associated with paired electrons. And then you have paramagnetism, which is the attraction associated with unpaired electrons. And this produces a much stronger effect than the weak diamagnetism of paired electrons, right? So basically what we're saying is that paramagnetism is a stronger phenomenon effect compared to diamagnetism. Diamagnetism is a weak repulsion, but paramagnetism is an attraction that these atoms or ions will have for an electric field. And then there's a third category, which is known as ferromagnetism, which is stronger than paramagnetism. And this is exhibited by iron and some other few substances. Now, for our purposes, we'll be discussing paramagnetism more so than the other 2, all right? So continuing, how do we determine whether or not an attractive force is acting on a substance? Well, we have this setup here which basically demonstrates how this works. So here we have the magnetic field that you can turn on or turn off. Here we have the substance in this capsule right here, and we can weigh the mass of the substance before turning on the magnetic field, right? And then when you turn on the magnetic field, then what happens? If it's paramagnetic, it's going to pull the substance within the capsule towards it, and therefore an increase in mass or weight would be registered. Of course, we know that the mass has not changed. Basically, what the weight is indicating, not only the mass of the substance, but also the fact that it's being attracted to the magnetic field. So as the statement here says, the mass appears to have increased, so this substance must be, and the answer would be paramagnetic. All right? And therefore, because it's paramagnetic, based on the definition that we said earlier, that means that this substance, whatever it is, has unpaired electrons. All right? So it's because of the presence of unpaired electrons in its electron configuration that this substance is paramagnetic, and therefore it displays the properties as shown or demonstrated in this experiment. Okay, so let's look at this question. This question says a sample of chlorine gas is found to be diamagnetic. In other words, it is repulsed as a result of paired electrons present. So the question is asking, can this gaseous sample be composed of individual chlorine atoms? Well, in order for us to do that, figure this out, we need to find the electronic configuration of chlorine, right? And the atomic number of chlorine, if I'm not mistaken, is 17. So therefore, 1s2, 2s2, 2p6, 3s2, 3p5 would be the electron configuration. Now, what I'm going to do is, I'm not so much concerned about these here. No, hold on. I'm sorry, this should be 3p5, not 6. So this should be 3p5. So what I'm concerned about, because all these are filled, all these subshells are filled, but the 3p5 subshell or the 3p subshell is not filled completely. So I'm just going to use the boxes, box diagram to represent the state of affairs when it comes to the 3p subshell. So the first electron will go here, the second will go here, third will go here, then the fourth, and then the fifth. So based on this electron configuration, we're going to have an unpaired electron, right? And if chlorine gas is made up of atoms, then because of this is being unpaired, that means that you'd expect this to be paramagnetic, right? If chlorine gas exists or composed of entirely chlorine atoms, then you'd expect this to be paramagnetic. Turns out that it's not paramagnetic, it's diamagnetic. So that tells you that the chlorine gas is not existing in nature as individual chlorine atoms. Instead, and you all should know this, chlorine is one of those elements that exist as a diatomic molecule, all right? So that's basically the answer to the question. The answer to the question is no, it's not composed of Cl atoms because it's not paramagnetic. It's not paramagnetic. Okay, so that's basically how you answer that question, all right? All right, continuing. So now we're going to look at periodic properties. So basically what you'll find, and I'm quite sure we touched on this earlier, I don't remember which chapter, I think it was chapter 2 or chapter 3. What you'll find is that in the periodic table, if you look at one element and move on to the other, you see that there's a variation in properties. And then the properties repeat when you get into the other period and so on. And this was first observed by Mendeleev, who was a Russian chemist. And what he discovered, now back then, they didn't know anything about the atomic structure. They didn't know anything about electrons, protons, or neutrons, right? The only thing in terms of the elements themselves that they knew was the atomic masses, right? So what he did was that he arranged the elements in order of increasing atomic masses. And what he discovered was that after so many elements, then the properties themselves repeat, all right? So he basically came up with a version of the periodic table, which was not complete by any means because there are some gaps in it, which basically represented elements that were not yet discovered, all right? So that's what Mendeleev discovered. And then some years passed, and then, of course, we come to our understanding of the modern version of our understanding of the atom, and we can now correlate the position in the periodic table with the electronic arrangement around the atom, especially with respect to the sublevels and so on. So as stated here, melting points, boiling points, hardness, density, physical state, and chemical reactivity are all periodic properties. In other words, after so many elements, you see some repeat in terms of properties or some gradual changes in terms of properties, all right? So what we're going to look at is how several properties vary as you go across a period and down a group, and how we can explain that based on the electron configurations, right? Now, the first property that we're going to discuss is what is known as the atomic radius, right? And there are a couple of ways of defining what the atomic radius is depending on the particular element. Now, if the element, let's say, is bonded to another, let's say one atom of the element is bonded to another atom of the element to form a diatomic molecule, then the radius is defined as the covalent radius, which is halfway the distance between the two nuclei, right? So if you know what the distance between the two nuclei is, divide that by 2, and that would be the covalent radius. So in this particular case, I don't remember what molecule this is, but in any case, the internuclear distance, the distance between the two nuclei, is 266 picometers. So therefore, the covalent radius is defined as 133 picometers, all right? So that's what happens, or that's how you define the covalent radius for an atom, which is part of a diatomic molecule. Now, in the case of metals, right, it's kind of similar. Basically, the distance between the two nuclei of adjacent atoms, if you divide it by 2, then that would be the metallic radius, right? And that is also used as a measure of the size of the atom, all right? So these are basically collectively the two things that we look at in order to establish the atomic radius, right? So with that said, let's see how we can examine or predict the type of trends that will take place in terms of the atomic radius as you go down a group or across a period. So let's deal with going down a group. Basically, what you'll find is that the atomic radius will increase as you go from top to bottom of any group, all right? So, and that is corresponding to the value of n increasing, right? N, of course, is a principal quantum number for the shells. So basically, the first shell electrons will be closer to the nucleus, and then the second shell electrons will be further away from the nucleus, and so on and so forth, all right? So that's basically what happens when it comes to the atomic radius. The atomic radius increases as you go from top to bottom of any group, all right? And as stated here, the principal quantum number n, which represents the energy level for the shell, it correlates to the distance of the electron from the nucleus. So basically, the further away from the nucleus the electron is, the greater the n value, and vice versa, all right? Okay, so that's one trend that we can observe when it comes to the atomic radius. As you go down the group, the atomic radius increases. Then we're going to look at what happens when you go from left to right of any period. And what you'll find is that the atomic radius will decrease going from left to right within a period. Now, why is that happening? Well, there are a couple of things that are occurring as you go from one atom to the next across the period left to right. Okay, so let me illustrate this by using the second period. Now, the second period starts with lithium, all right? And if you look at the electronic structure of lithium, there are 2 electrons in the first shell and then 1 electron in the second shell, right? Now, that 1 electron in the second shell will be experiencing 2 forces, right? So I'm going to use a Bohr model, even though the Bohr model is not actually, what's the word I'm looking for? Not in line with what we understand now about the structure of the atom. But we can use it to illustrate this. So in the case of lithium, you have 2 electrons in the closest to the nucleus, right? And then in the next shell, second shell, you have 1 electron, all right? So think about this. There are 2 forces at work. There's the attractive force between the nucleus and the surrounding electrons. But there's also a repulsive force between this electron, which is further away, and these 2 electrons, which are closer to the nucleus, right? So there's a term that is used for that repulsive force. We say that this electron here is experiencing a screening effect. Screening effect that is caused by the repulsion between it and the electrons which are closer to the nucleus, right? So the screening effect is in effect, in addition to the fact that you have the attractive force between the nucleus, which is positive, and the electrons, right? Now, oh, yes, sir.
Would you say that the effective nuclear charge increasing, is that like, that's dealing with strong nuclear force, right? Which is what holds the atom together in general?
Exactly. And the effective nuclear charge is related to the screening effect in that the outer electron is not experiencing the full nuclear charge, right? Or the full pull of the nuclear charge, right? So the effective nuclear charge is what the outer electron is experiencing, all right? Now, let's understand what's happening here as you go from one element to the next across period 2. And this will apply to the other periods as well. What are the changes that are taking place as you go from one element to the next? 1, you're adding a proton to the nucleus, right? So if you go from lithium, which has 3 protons, to beryllium, which has 4 protons, then what's the next one? Boron, which has 5 protons, and so on, right? So you're increasing the nuclear charge. At the same time, you're adding electrons to the outer shell, right? So you add 1 proton to the nucleus. At the same time, you're adding an electron to the outer shell, right? So what's the consequence of that? The consequence of that is that the screening effect is still the same, right? So therefore, the result would be that the outer electrons, in fact, all the electrons will be pulled closer and closer to the nucleus as you go from lithium to beryllium to boron to carbon and so on, right? And as a result, the atom itself becomes smaller, right?
The screening effect is just the atoms being drawn in?
Well, the screening effect is basically the inner core electrons still repelling the outer electrons.
Oh, okay.
Right? But that screening effect is constant as you go from one, because like in the case of period 2, there are only 2 electrons in the inner shell. So those 2 electrons will be screening all the electrons that are added to the outer shell. Right. So the screening effect is still the same. The difference is that you're adding protons to the nucleus, and therefore the effect will be that it will pull the electrons closer to the nucleus, and therefore reducing the atomic size. And that's the reason why the atomic size decreases as you go from left to right.
So the distance between the valence electrons and the core electrons doesn't change, but they both get drawn in.
Exactly. All right. So that's what happens as you go from one atom to the next across a period. The atomic size decreases. All right. And that is demonstrated in this example here. If you compare sodium to magnesium, the nuclear charge is increasing from 11 to 12, right? Sodium and magnesium are in period 3, right? So basically, as a result of that, the magnesium atom would be smaller because the nuclear charge is larger and will pull the surrounding electrons closer to the nucleus, and therefore the magnesium would have a smaller size compared to the sodium atom, all right? So that's basically what happens as you go from left to right of any period, the atomic radius will decrease. And this here is a graphical demonstration of that. And you can see, well, let me just explain what happens here. You have the atomic radius plotted on the y-axis, the atomic number plotted on the x-axis, and this line here, or this curve, represents what happens as far as period 2 is concerned. This is for period 3. Now, in period 4 and the rest of them, there's a bit of a kink that occurs here, here, and in this case, there are 2 kinks here and here, right? I won't go into that. There are reasons for that, which I won't get into right now. It's a bit beyond our scope at this level, all right? But generally speaking, this is what you'll find. As you go from one atom to the next, left to right, the atomic size decreases.
Does it have to do with electronegativity, or is that a different?
No, no,
Different effect entirely.
right. It has to do with basically overlap between different shells and so on. It's long and
That's it.
yes. Okay, so let's see if we can answer these questions. So this question says, using only a periodic table, and I'm going to need your guys' help. In fact, I should have brought a copy of mine here. Using a periodic table, and only a periodic table, arrange each of the set of elements in order of increasing atomic radius. Now, let's deal with the A part first, right? Now, in the case of A, you have magnesium, sulfur, and silicon. And if I'm not mistaken, please confirm this. Those elements are in the same period, right?
Yes, sir.
Okay. So basically, magnesium would be to the extreme left, right? Sulfur would be to the right, and silicon is in the middle, if I remember correctly, right? Okay, good. So remember now, the size decreases as you go from left to right. So, and remember now, the question says that you're going to put them in order of increasing atomic radius, which means that you have to start from the smallest to the largest, right? So of these three, which would be the smallest?
Not magnesium, sulfur.
Sulfur, yes. Sulfur would be the smallest because sulfur would be to the extreme right. Which would be the next in line?
Silicon.
Silicon and then magnesium, right? So that would be the answer for A, okay? Okay, in the case of B, they gave you arsenic, nitrogen, and phosphorus. And I'm sure that those are in the same group, the same column, right? Group 5, all right? So if you remember, we said going down a group, the atomic size will increase. So with that said, which would be the smallest in this series? Arsenic, nitrogen, or phosphorus? Nitrogen, followed by?
Phosphorus.
Okay, yeah, you're right. And then followed by arsenic. Very good. All right. So let's look at C. In the case of C, they gave us arsenic, antimony, and selenium. Now, if I remember correctly, let me see here.
They're all next to each other.
Okay.
You've got arsenic, and then to the right of it is selenium, and then right below it is antimony.
So arsenic is here. And what's
Selenium.
selenium is here?
Yes, sir.
And antimony is down here, right?
Yes, sir.
Oh, okay. All right. So basically, all right. So which of these would you expect to be the smallest? We're starting from the smallest to the largest.
Be arsenic.
Arsenic, followed by?
Which increases faster.
Ah, good question. The one that increases fast is the group going down. So that means that,
Selenium.
exactly, selenium, followed by antimony. All right, and that's it, right? So that's how you can determine the order of atomic radius based on the positions of the different elements in the periodic table.
Wait, it's increasing.
Oh, wait a minute,
So
hold
it would
on.
be selenium and then arsenic.
Yeah,
and
thank
then
you, thank you. Yeah, you're right, actually. Thank you for pointing that out. So it would be arsenic, then oh, what am I doing? I erased the wrong thing. Remind me again. So it was arsenic here, and then
To the right of it is selenium. And
selenium, and then antimony, right?
Yes. So it would be selenium.
So
Then
it'd be
arsenic.
selenium first.
and-
Yeah, it would be selenium first, because selenium is the smallest. Whoops, come on. So it's going to be selenium first, and then arsenic, and then antimony. Okay, very good. Now, Okay, now we're going to talk about the size of ions, right? Of course, just as how we defined the atomic radius for metals and what do you call it? Bimolecular molecules, we have to do the same thing for ions, right? So let's define the ionic radius, which is the portion of the distance between the nuclei occupied by that ion, right? So here's an example. For magnesium oxide, the distance between the two nuclei is this right here, 205 picometers. And when they look at it further, they establish that the radius of the magnesium ion is 65 picometers. That of the oxide ion is 140 picometers. So those two add up to an internuclear distance of 205 picometers, all right? So we're going to look at, firstly, comparing the size of the ions to the size of the atoms from which they're formed, all right? So in the case of cations, and of course we all know that cations are formed as a result of electrons being removed from atoms. So what happens to the size of the ion that is formed? Well, what you'll find is that the size of the ions are smaller compared to the size of the atoms from which they're formed, all right? So basically, what happens is that to form, let's say, for example, you're going from sodium to sodium plus, right? Basically, you're removing one electron, right? What's going to happen? There'll be less repulsion between the electrons that are remaining, and therefore they will be drawn closer to the nucleus, right? So the sodium ion will be smaller in size as a result compared to the sodium atom. And that is true pretty much right across the board for all ions when you compare their sizes to their atoms. So here's another example. Magnesium, it has a radius of 160 picometers, but when you compare that to magnesium ions, it's 65 picometers. So that's more than double, or I should say that's more than half the size when you compare the magnesium ion to the magnesium atom, all right? So that is basically true pretty much when you look at the relationship between cations and anions. I'm sorry, between cations and the atoms from which they're formed. Now, when it comes to anions, the opposite is true. Anions will be larger in size compared to the atoms from which they're formed. And the reason why is because when you add electrons to an atom, you're increasing repulsion between the electrons, and therefore it will swell up and get to a larger size. I thought I had some data. Oh, here's one here. Okay. So if you compare chlorine, which has a radius of 99 picometers, and you add an electron to it, the size of the corresponding anion is almost double, 181 picometers, all right? So that's basically what happens when you have an atom gaining electrons to form an anion. The anionic size will be larger compared to the atomic size of the element from which it is formed, right? Now, at this juncture, I want to introduce to you this concept of isoelectronic, this term. Basically, it's used to compare two or more atoms, ions, etc., right? Basically, if you have an isoelectronic series of structures, atoms and ions, what that means is that they have the same electron configuration, right? Now, if you were to compare them, you can see that there is a correlation between the size of these structures and their nuclear charge, right? Basically, the size decreases with effective nuclear charge. So let me give one example. Let's say, for example, you want to compare the sodium ion to neon, right? And you want to ask yourself which one has a smaller size or greater size, right? What I would do in order to establish that is look at the number of electrons that is present in the sodium, I'm sorry, I would look at the number of protons first in the sodium ion. That would be 11, right? So for protons, that would be 11. In the case of neon, the number of protons will be 10. But they will have the same number of electrons, which would be 10 electrons, right? So basically, because sodium will have a greater number of protons, it will have a higher nuclear charge and would pull the electrons closer to the nucleus compared to the neon atom. So therefore, the result of that, we can say that the sodium ion will be smaller compared to the neon atom. They have the same number of electrons surrounding the nucleus, but sodium has a greater nuclear charge, and therefore it will pull the electrons closer to the nucleus and therefore reduce the size compared to the neon atom. All right? So that's basically how that is done. Okay, any questions about this? Any questions? Any questions? All right, so this chart here basically is a summary of what we just discussed in terms of atomic and ionic sizes, all right? And all that we have discussed before in terms of trends going across a period, going down a group, can be seen in this particular chart. So just to give you an example, if you take group 2A, for example, remember we said that the atomic size increases as you go down the group. And you can see this. Oh, by the way, I should mention that what color is this? Purple. The purple spheres represent the atoms. The orange spheres represents cations. And the blue spheres represents anions, all right? So that's that. So as I said before, going down any group, the atomic size increases. And you can see that in, for example, group 2A, right? At the top of the group, you have beryllium. It has a size of 111 picometers. And then the next in line is magnesium, which is 160. And then the next in line is calcium, which is 197. Then 215 for strontium and 217 for barium, right? So you see a change or an increase in the atomic size as you go down the group. You also see a decrease in atomic size as you go across any period. So if you were to take, for example, period 3, which starts with sodium, right? Its size is 186. And then for magnesium, it's 160. And then 143 for aluminum and so on. And you see that it decreases until you get to chlorine, for which the atomic size is 99, all right? And then you can see the comparison between the cation and the atom from which it is formed, right? So for example, this is 152 for lithium atom. 59 would be the radius for the lithium ion, for example, right? And you see that demonstrated in all the other instances where you're given the size of the cation compared to the size of the atom. And then over here on the non-metallic side, you see the opposite is true. The size of the anion is greater than the size of the atom from which it is formed. So just to choose some arbitrary examples, in the case of nitrogen, the nitrogen atom is 75 picometers in size. The nitride ion is 171 picometers in size. So that's just one example. And you see that trend for the other atoms compared to their anions. The anions will always be larger compared to the size of the atoms, all right? Okay, so another example to look at. Refer to the periodic table only and do not cheat by looking at the other previous figure. It says arrange the following species in expected order of increasing radius, all right? So what I would do, again, I would look at the number of protons versus electrons, because if I can identify an isoelectronic series, then that makes life a lot easier. All I have to do is look at the number of protons. The one with the greater number of protons for the same number of electrons would be the smaller ones, right? So in the case of calcium, let me do the protons first. So in the case of calcium, the number of protons would be 20. In the case of Fe3 plus, what's the atomic number of Fe? I'm sorry? Okay, so this would be 26. Potassium would be 19, and sulfide would be 16, if I remember correctly. And what is selenium? Se.
Selenium, 34.
34, okay. So those are the number of protons for each of them. Now let's look at the number of electrons. In the case of calcium, I would have to remove 2 electrons from 20, so that leaves 18. In the case of iron, that would be 23. In the case of potassium, that would be 18. In the case of sulfide, I'm adding 2 electrons, so that would be 18. And in the case of selenide, that would be 36, right? And immediately, I identify these 3 as being isoelectronic. They have the same number of electrons, right? So based on that, I can look at the number of protons to establish the order. And the one that would be smallest would be the calcium 2 plus, because it has the highest nuclear charge among those three, followed by potassium plus, followed by sulfide. All right. So the question now becomes, where do I put the other two, the selenide and the iron 3 plus? All right. And as far as, oh, wait a minute. Okay. As far as the selenide is concerned, if you look at where selenium is in the periodic table compared to sulfur, it's below, right? So that means that its size would be larger than sulfide, right? So I would put selenide right here, right? And then as far as the Fe3 plus is concerned, Fe3 plus is in the same period as calcium, right? And it has a higher nuclear charge, even though it has 23 electrons. So I would put Fe3 plus here. And that would be it. All right? So that would be the order of the series in terms of the atomic size. Okay, any questions about this? Any questions? All right. Before we move on, let's go to the assignments. I think we are now able to do some questions that we haven't done before. Okay, so I think we did part A, right? Okay. Excuse me. So we're on to part B. And in part B, it's asking, write the complete electron configuration for each of the following ions and determine which one possesses the noble gas configurations. In other words, which ones obey the octet rule or the duet rule by having a complete outer shell. So in the case of chloride, the atomic number is 17. So therefore, 1s2, 2s2, 2p6, 3s2, 3p5, right? So that's for the atom. So to get from the chlorine to the chloride, what do? We add 1 electron to this, so this becomes 6, right? And the question is asking if it has a noble gas configuration, and the answer is yes, because all the shells are completely full. In fact, this has the same noble gas configuration as argon, right? So the answer is yes, because all shells are filled completely. All right? Okay, so that's that. That's for chloride. In the case of cobalt, now let me see. Cobalt, what's the atomic number of cobalt? 27. So that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s 2, 3d5. All right, so that's for the cobalt atom. All right, for the cobalt ion, cobalt 3 plus ion, we need to remove 3 electrons. So remember now, the electrons are first removed from the highest shell, right? Which would mean that you remove these two, right? And then the third electron will be removed from here. So that becomes 3d4. When this shell lost its electrons, so therefore that will disappear In fact, let me just do this here. So the answer will be 3D4 at the end. All right? Okay. And then in the case of cobalt 2+, well, that's easy based on what we have here. Basically, in the case of cobalt 2+, it will be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5. And that would be it for cobalt 2+. So that's relatively easy. For the next one, let me clear this first. For the next one, chromium 3+, can somebody tell me what the atomic number of chromium is, please?
Chromium?
Cr. 24, okay. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, that's 20, and then 3d4. Now here's where you need to be careful, because this is one of those exceptions to the Aufbau principle that I talked about. You notice you have 4s2 here and 3d4. That actually should be 4s1 and 3d5. Because if you remember, I said that even though I didn't go into any detail about it, it turns out that half-filled and completely filled subshells are more stable than otherwise, right? So this would be the electronic configuration for the chromium atom. Now, to get the chromium ion, we would have to remove this electron here. And that's chromium 3, and then we have to remove 2 from here. So that becomes 3d3, and this 4s sublevel will not be there, right? So the answer would be this. All right? Okay, any questions about this one? Any questions? Any questions? Okay, the next one, titanium. What's the atomic number of titanium? 23? 22? Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d2. No, 4s2. What am I saying? 4s2, and then 3d2. All right? So that's 20 plus 2, 20. Okay, good. So for titanium 3+, you'd have to remove these two and remove 1 from here. So basically, the final answer is going to be 3d1 at the end. All right? And by the way, all of these that we have done so far, with the exception of the first one, do not have a noble gas configuration. All right? So that's why I didn't say anything about that. Now let's look at lithium. Lithium is the easiest one because lithium has an atomic number of 3. So that's 1s2, 2s1. So to get the lithium ion, all we have to do is remove this. So basically that means that the electronic configuration of the lithium ion is 1s2. And this has a noble gas configuration because the noble gas that is closest to is helium. So this is the same thing as the noble gas configuration of helium, right? So that's that. Any questions? All right. Let's see here. Oh, let me get rid of this here. Oh, okay. Now this one is asking you to arrange each set in order of increasing sizes. So remember, increasing means from the smallest to the largest, right? So the first one is this right here. So let me hear what you think is the answer to this one. Which one will come first?
The smallest,
Which will be the smallest?
Fe3 plus.
Exactly. Fe3 plus will be the smallest, followed by
Fe2.
Fe2 plus, followed by Fe. All right. And of course, the reason for that is that every time you remove an electron, the size decreases, right? So the one with the highest charge, everything else being the same, would be the smallest. Okay, so that's relatively easy. What about B? Now, in the case of B, you're given sulfide, arsenic, and selenide, right? So as I said before, when it comes to things like these, I like to look at the number of protons and electrons, right? So as far as the protons are concerned, sulfur has an atomic number of 16, argon has an atomic number of 18, and what's selenium again? What's the atomic number?
34.
34, all right? Now, in terms of electrons, the sulfide will have 18, excuse me. Argon will have 18 as well. The selenide has 36, right? So we can compare these two right here. They have the same number of electrons and different number of protons. Argon has a greater nuclear charge, so argon will be smaller compared to the sulfide ion. So the question now becomes, where does the selenide ends up? And where do you think it ends up? The selenide, based on its position in the periodic table.
It's gonna be the so it's gonna be the largest radii, right?
Exactly. It's going to be greater than sulfide because the selenide is right below sulfide in the same group, right? So that would be the order. All right. Okay. Any questions about that? Any questions? Any questions? All right. Let me clear this here. And let's look at the next one, C. Now, in the case of C, they gave you aluminum chloride, sulfide, and potassium ion. So again, I like to look at the number of protons versus electrons. So let me start off with the protons here. So sulfur have 16, chlorine have 17, potassium has 19, and calcium has 20, right? But in terms of the electrons, sulfide would be 18 electrons, chloride would be 18, potassium would be 19, and actually 18 as well, I'm sorry, and calcium will be 18. So this one is relatively easy. Calcium will be 18, right? So this one will be relatively easy because they all have the same number of electrons, but they have different nuclear charges, all right? So based on that, you should be able to tell me the order. Which would be the smallest?
Calcium.
Calcium, 2 plus, followed by potassium plus, followed by chloride, followed by sulfide. And that's it. All right. Okay, any questions about this one? Any questions? Any questions? All right, let me clear this here and scroll down. Oh, that's it? Hold on.
You didn't do C.
Oh, I skipped C. Oh, did I? Okay, my bad. Okay, so in the case of C, again, I'm going to look at the number of protons versus electrons. So aluminum, if I remember correctly, its atomic number is 13. Chloride is 17. Sulfide is 16. And potassium plus would be 19, right? So in terms of the electrons, aluminum will have the same number of electrons as protons. So that's 13. Chloride will have 18 electrons. Sulfide will have 18 electrons. Potassium has 18 electrons, right? So we can tell straight off the order of these three because they have the same number of electrons, different number of protons. So which one in this series of three would be the smallest?
Potassium.
Potassium plus. Which would be next in line?
Not sulfide, chloride.
Yes, chloride would be next in line, and then sulfide. So now it begs the question, where does aluminum fall? Now, aluminum is in period 2, right? right, which is above the period that these ions are present in. So basically, aluminum belongs here, right? It will be small in size. All right. Okay. I'm sorry.
You said in the same period?
No, aluminum is in period 2, right?
No, aluminum's in period 3.
And where's potassium? Oh, I'm sorry. Aluminum's in period 3. Potassium and chloride is in period
No, chloride, sulfur, and aluminum are all in the same.
same period, right?
Yes, sir.
And
then
potassium is in period 4. Okay. So yeah, the answer is still right because aluminum is to the
it's still small. Right?
yeah.
Yeah.
Hold on, let me rethink that. Aluminum.
They increase as you go from left. They decrease as you go from left to right, so it's going to
Yeah,
be
but-
larger.
Mm,
It would wait.
the atomic size decreases going from left to right, right? Aluminum is in the same period as chlorine and sulfur.
It's going to be the largest because it gets bigger as you move up and as you move left. It's above potassium
You're,
and to the left
you're right,
of
exactly.
chlorine and
So
sulfur.
aluminum would go here. My bad. You're absolutely right. So aluminum would be here. I'm going to recheck this, but I'm quite sure you're right. All right. Okay. So that's basically how that one is done. Next class, I'm going to make sure if it's not right, I'll make sure let you know. But I'm very sure now that you mention it, I'm very sure that that's correct. All right. So let me clear this. Oh, it's 12:08. I don't think we can do anything else. Let me just check something here. Okay. I'm going to stop for today. All right. So that's pretty much it. If you have any questions, I'll be available today in my office for office hours. But that's pretty much it for today, folks. And enjoy your weekend. Oh, and remember that Tuesday is a holiday, so the college will be closed, which I kind of find to be weird on a Tuesday. I prefer my holiday on like a Monday or a Friday.
I think it's because Veterans Day is a set day rather than like
Right, yeah,
I think Memorial Day is like the first Monday of
exactly.
I think May.
Yeah, they need to change that.
Yeah.
Oh, well. Oh, somebody has a question online. Let me see, let me see. Oh, I didn't. I apologize for that. Somebody said that I didn't post the PowerPoint slides for this chapter. So let me take care of that now. Let me go. I apologize for that. Okay, so now it is published. All right. Okay, so for you guys in Zoom, I'm signing off. Oh, you're welcome, Mr. Hernandez. Oh, man, you guys are just coming in with your messages at the end. Okay, let me see here. Somebody was saying that I didn't get them for attendance. So let me take care of that now. Okay, who was it that said that? Wilbert. Okay, I got you now. While I'm here, let me see if there are any other persons I didn't get. Is Barner here? Davis? Nope. Hernandez? No.
I just need to ask you something.
Oh, okay. Hernandez. I know Hernandez was here, I think. Let me see. Jernigan. I don't see Jernigan. Nelson. I don't see Nelson. Osorio. I don't see Osorio. Fan is here. Okay, so I see fan. And oh, I got you. Oh, you're the last name here, Zoretka. Okay, so that's it. I'll see you guys next Wednesday. All right.